In this video, we're going to look at some more examples about computing partial derivatives algebraically. So the first example, find the four second-order partial derivatives of the function WPR equals e to the 2p times r plus 6pr to the seventh. This is just a more complicated function of two variables. We're going to deal with it in the same way we did in the previous video. So first we need to find the two first-order partial derivatives. That is going to be W sub P and W sub R. So this is going to be the partial derivative with respect to P of e to the 2p times r plus 6p r to the seventh. So when we're doing this, everything with r is just a constant. So we're just going to bring it along for the ride each step of the way. So the first derivative, e to the 2p times r, is going to be an r on the outside times the derivative of e to the 2p. And the derivative of e to the 2p requires a quick use of the chain rule. So that derivative is going to be e to the 2p times the derivative of the outside, or of the inside, which is 2, and then times the r, which comes along for the ride as a constant, plus the derivative of 6p r to the seventh. R to the seventh is a constant, 6 is just a constant, times p, so that's just going to give us a 6r to the seventh, the constant there. So rewriting this in a nice way, this is equal to 2r e to the 2p plus 6r to the seventh. That is w sub p. Now let's find w sub r. That's the derivative with respect to r, the partial with respect to r. And in this case, the e to the 2p and the 6p are constants. So the derivative is just going to be e to the 2p is a constant times r is just going to give us e to the 2p. And 6p r to the seventh is going to give us the constant 6p times the derivative of r to the seventh, which is 7r to the sixth. So writing that in a nice way, that's going to be e to the 2p plus 42p r to the seventh. All right, now we need to find the second order partial derivatives. So we have w sub p, that's going to be the partial derivative with respect to p of w sub p, which is the partial derivative with respect to p of 2r e to the 2p plus 6r to the seventh. Let's label our constants here so we get used to this. Anything with an r is a constant. So the derivative, the first part's going to have this 2r come along for the ride, and then the derivative of e to the 2p, which is 2e to the 2p, as we did that in the previous problem with the chain rule. And then the derivative of 6r to the seventh is just 0, as it's a constant. So writing this in a nice way, this is just going to be equal to 4r e to the 2p. Now let's find w sub pr, and note that this is going to be the exact same thing as w sub rp. It doesn't matter which order we do it, we're going to get the same thing either way. And that's also a good check if you want to see if something went right, because if they're not the same, that's an issue. So WPR is the derivative with respect to r of w sub p. That's going to be the derivative with respect to r of 2r e to the 2p plus 6r to the 7th. And we note that this e to the 2p is a constant. So the constant's going to come along for the ride. And we have the derivative of 2r is just 2. And 6r to the 7th is just a normal derivative. That's going to give us a 42r to the 6th. Taking the 7 down out in front times the 6th. Let's verify this is the same thing as WRP by just doing that calculation real quick. So WRP is going to be the partial with respect to P of W sub R, partial with respect to P of e to the 2p plus 42p r to the 7th. And note that this r to the 7th is a constant. So the derivative here should be a normal derivative. E to the 2p is 2e to the 2p. And then that r to the 7th is a constant. 42 is a constant. And we can see the little mistake that I made as well. Here in w sub r, I wrote r to the 7th when I should have r to the 6th. So this should be an r to the 7th here. And there is our 42 r to the 6th as r to the 6th as a constant times p. So that's our derivative. And then there is our check that we did something correct. Our derivative in both cases is 2e to the 2p plus 42 r to the 6th. That is always going to happen. So you only really need to find one of those to find both, but it can be a good check, as we just saw in real time, that something went correct, right? I made a little error changing the 6 to a 7 for no reason, and I caught that error because I know that those two things should be the same. Finally, let's find the last partial derivative, which is r sub r. That is the partial with respect to r of w sub r, partial with respect to r of e to the 2p plus 42p r to the 6th. E to the 2p is a constant. 42p is a constant. The derivative of a constant is 0. So it's just going to be 42p, which comes along for the ride, times 6r to the 5th, which is going to be 42 times 6, which is 132 pr to the 5th. So there are our 4 second order partial derivatives, noting that the middle two are the same as they're always going to be if we have continuous functions, which we're almost always going to have. All right, let's look at another example. So find all points where the partial derivatives of f of x, y are both 0, given our function. This is something extra on top of just finding the partial derivatives, though the first thing we need to do is find the partial derivatives. So let's find our two partial derivatives, f sub x and f sub y. F sub x is the partial with respect to x of x squared plus 4x plus y squared. This y squared is a constant with respect to x. So this derivative is going to be 2x, the derivative of x squared, plus 4, the derivative of 4x, plus 0, the derivative of y squared, which is a constant with respect to x. Let's find the derivative with respect to y in a similar way. This is the derivative partial with respect to y of x squared plus 4x plus y squared. Here we have a constant, and then the y squared. So this should be equal to a 0 plus 0 plus the derivative of y squared, which is 2y. So writing this in a nice way, this is 2x plus 4, and here is 2y. So we're going to try to find all points where these partial derivatives are both 0. So that means that we're going to set both of these functions equal to 0. We want f sub x equal to 0, and f sub y equal to 0. So f sub x is 2x plus 4. Set that equal to 0. That's going to give us a 2x equals negative 4. X is equal to negative 2 when we divide by 2. And f sub y being 0 is going to be 2y equals 0. So y is going to be 0. So this means that all the points where the partial derivative is going to be 0 is going to be only one point, the point where x is negative 2 and y is 0. There's other examples we could do here where you would get more points than just that would be 0, but it's just a matter of solving both of those equations and kind of putting them together. And there's something special about both derivatives being 0. We're going to look at this in the next section. This is why we're introducing it right now. But we know that we can find the min and the max of a function by setting the derivative equal to 0. And we can find the min and max of a function of two variables in a similar sort of way by setting both partial derivatives equal to 0. So this is something we're going to do a lot in the next couple of sections. All right, our next example here. A company's production output, P, is given in tons and is a function of the number of workers, N, and the value of the equipment, capital V, in the units of $25,000. The production function for the company is P, which is a function of N and V, the number of workers and the value of the equipment, is 5 N to the 0.75 times V to the 0.25. We're going to find and interpret the values of F and the partial derivatives when the company currently employs 85 workers and has equipment worth $750,000. So our first order of business is saying that what we're looking at here is specifically 85 workers means that N is 85 and has value of equipment $750,000. Since we're looking at in units of $25,000, this is V equal to 750,000 divided by 25,000, which would give us a value of V equals 30. So we are trying to find and interpret three things: F of 8530, and then F sub N of 8530, and F sub V of 8530. So let's start with just F of 8530, as we already have that here, and we know how to deal with that. So F of 8530, we can just plug these values in. It's going to give us 5. N is 85, so 85 to the 0.75 times 30 to the 0.25 will give us a value of about 327 tons of production. So again, what does this mean? This means that if we have 85 workers and $750,000 worth of equipment, we should expect to produce 730 or 327 tons of material. All right, now we need to find the derivatives and interpret what those mean in terms of the context. So first thing is we need to find F sub capital N. So the derivative here is going to be the derivative with respect to N of 5N to the 0.75, v to the 0.25. And it's important to note that all of this is just a constant. So it's going to come along for the ride, v, or 5v 0.25. And then the derivative of n to the 0.75 is just using the power rule. That's going to bring the power down out in front times n, and then decrease the power by 1. We'll have a negative 0.25 as the power there. And what I really care about is not so much that, but plugging in 85 and 30 into that function to give us 5, 30 to the 0.25 times 0.75, 85 to the negative 0.25, which is about 2.9. So what this means in the context, as we're thinking about in terms of n, this says that currently if we increase the number of workers by 1, the production should go up 2.9 tons. Let's do the same thing now for the derivative with respect to v. That's the partial with respect to v of 5n to the 0.75, v to the 0.25. But now everything except for the v is a constant. We take the derivative, the constant's going to come out in front. And we're going to take the derivative of v in our normal kind of fashion, which should be bring the power down out in front times v and then decrease the power by 1. We get a negative 0.75. And again, what we care about here is the value when we plug in 85 and 30 should be 5, 85 to the 0.75 times 0.25, 30 to the negative 0.75, which is about 2.7. So what this means is, again, currently, if we increase the value of the equipment by 1 unit of V, so that's by $25,000, the production increases by 2.7 tons. So note that that $25,000 is because 1 unit of V is 25,000. All right, one last example here. It's going to be going backwards through this derivative process. Find a function f of xy that has the following partial derivatives. Sometimes it's very useful trying to go backwards through this process to try to think about the actual derivative process itself. Note that what we're actually doing here is taking antiderivatives of our partial derivatives, but we're not really going to think about antiderivatives right now. This is just an exercise to help us to figure out partial derivatives. So we're just going to try to play around with this. If f sub x, xy is 24x squared y squared plus 3, let's think about all the constants that we have there. We have this 24, we have this y squared, we have this 3. we take the antiderivative of our function. We have f of xy is going to be something with 24y squared and a something with a 3. And note that this something with a 3 has to be just x. As we're taking the derivative with respect to x will give us 3. That means we have a 3x left over. And if we have an x squared in our term, that means that we have to have a x cubed in our original. We're just going to take the antiderivative of x squared, which is 1/3 x cubed, plus some constant c. So putting this all together, this is going to be an 8y squared x cubed plus 3x plus some constant c. And let's do the same thing with the partial with respect to y. So here our constants are this 4 and this 16x cubed. So when we find our original function, we find the antiderivative. We know that that's going to come along for the ride, the 16x cubed times something, and then the 4 times something. This 4 has to be a 4y. Now we're going to take the antiderivative of that y, which is the 1/2 y squared, plus some constant. So this will be an 8x cubed y squared plus 4y plus c. Now note that these two functions have to be the same. It's the same function that we're finding. So it all kind of comes down to this constant. And this constant could involve y. And this constant could involve x. And we actually know that in order for this to work, this function has to be a 4y plus maybe some other constant. This guy has to be a 3x plus some other constant maybe. And altogether we get f of xy is going to have to be 8y squared x cubed. That was the same for both of these. Plus 3x plus 4y, and then maybe plus some constant c, just a number. And it'd be good exercise to go through the derivative and make sure that you get those partial derivatives out there. This is looking ahead, thinking about antiderivatives, but it's a good exercise to think about the derivatives in this case.